Let's think about chemistry for a second. It's kind of like a cosmic kitchen, right? Chemical reactions are just recipes where you combine ingredients to make something totally new. But here's the thing. Unlike your grandma's secret cookie recipe, these chemical recipes have to follow one single, absolutely unbreakable rule, a rule that governs the entire universe. So let's pull up a stool and see how it all works.
All right, here's how we're going to break this down. First, we'll get a handle on that one universal law that everything else is built on. Then we'll learn the basic rules of the game. We'll practice with a pretty straightforward trial and error method, and then we're going to level up to a much more powerful algebraic technique. And finally, to wrap it all up, we'll see why this skill is so much more than a classroom exercise. It actually impacts the world around us every single day.
Okay, so let's start with the absolute foundation. And this isn't just some rule for chemistry class. No, this is a fundamental principle of how our entire reality operates.
What that really means is you can't just create atoms out of thin air, and you can't make them vanish into nothing. It's impossible. Everything you start with has to be there at the end. The atoms just, well, they get rearranged into new molecules. It's like shuffling a deck of cards. You get a new hand, but all 52 cards are still in the deck. They're just in a different order.
And that right there is the whole problem we're trying to solve. Sometimes, when we first write down a chemical reaction, it looks like we've lost some atoms, or maybe magically created new ones. And since we know that can't happen, it just means our recipe, our chemical equation, is incomplete. It needs to be balanced.
So before we jump in and start balancing things, we gotta know the rules of the game. There are things we are allowed to change, and one very, very important thing that we absolutely cannot touch.
Okay, this is probably the single most important rule, and it's where almost everyone gets tripped up at first. Let's go back to our recipe analogy. Changing a coefficient, that's the big number in front of a molecule. That's like deciding to use 2 cups of flour instead of 1. You're just changing the amount. But changing a subscript, the little number inside a molecule's formula, that's like swapping your flour for sugar. You've just changed the fundamental ingredient. H2O is water. H2O2 is hydrogen peroxide. Totally different things. So rule number 1, we can only change the amounts, never the ingredients. All right, so how do we actually do this? Well, the first method we're going to look at is the most common one. It's called balancing by inspection, which, is really just a fancy way of saying we're going to use a little logic and some good old-fashioned trial and error to solve the puzzle.
Let's start with a classic, probably the most famous chemical reaction out there. Hydrogen gas plus oxygen gas makes water. But as it's written right here, it's wrong. It's unbalanced. It's breaking that universal law we just talked about.
Let's do a quick head count, some atom accounting, if you will. On the left side, the reactant side, we start with 2 hydrogen atoms and 2 oxygen atoms. Simple enough. But on the right, the product side, we have 2 hydrogens and only 1 oxygen. Wait a minute. An oxygen atom just vanished. That can't happen. We've got to fix this.
Okay, so the oxygen is the problem, right? Let's focus there. To get 2 oxygen atoms on the right side, our only move is to make 2 water molecules. So we do that by sticking a big 2 right in front of the H2O. Our equation now says we're making 2 water molecules. Okay, great. Let's do another head count and see where we are now.
Okay, so good news and bad news. The good news is we fixed the oxygen. We've got 2 on each side. Awesome. The bad news is we accidentally created a new problem. By making 2 water molecules, we now have 4 hydrogen atoms on the right, but we still only have 2 on the left, so we're still not balanced.
But luckily, this one's an easy fix. The hydrogen gas on the left is all by itself, so we can just put a 2 in front of it and it won't mess anything else up. And voila! Let's do a final check. 4 hydrogens on the left, 4 on the right. 2 oxygens on the left, 2 on the right. It is perfectly balanced. The law of the universe is satisfied.
So inspection is great for these simpler puzzles. But what about when things get messy, when the reactions get more complex? Trying to guess and check can get, well, really frustrating really fast. So now, let's level up. Let's look at a much more powerful, systematic method that will always get you the right answer. Algebra. So check this out. The combustion of butane. It's definitely a bit trickier. So instead of just guessing, we're going to assign a variable, A, B, C, and D, to stand in for each coefficient. Our whole goal is just to solve for those 4 variables. And now we just translate our atom accounting into algebra. For every single element, we create a simple equation.
For carbon, you see the little 4 in C4H10, so that's 4 times A on the left, and that has to equal C on the right. For hydrogen, 10 times A has to equal 2 times D. And for oxygen, 2 times B has to equal 2 times C plus D. Now, you might be looking at that and thinking, hold on, 3 equations and 4 unknowns? That's impossible to solve. But here's the secret. We're just looking for the simplest ratio. So we can just pick a starting point. Let's just say A equals 1. Well, if A is 1, our first 2 equations instantly tell us that C equals 4 and D equals 5. Easy. Now we plug those into the last equation to find B. A little bit of math, and we get B equals 13 over 2. Uh-oh, a fraction. You can't have half a molecule, but no sweat, that's an easy fix. We just multiply everything by 2 to get rid of it.
And that gives us our final coefficients: 2, 13, 8, and 10. And there you have it. No guesswork, no crossing your fingers. Just a clean, systematic process that nails it every single time. Okay, so what? Why are we doing all this? Why does this even matter outside of a chemistry class? Well, it matters because these balanced equations, these cosmic recipes, they tell us the exact ratios of everything involved. And knowing those ratios is the key to, well, everything, from making medicine to mixing rocket fuel and, yes, understanding our impact on the climate. Just take a look at this. This right here. This is what's happening inside a car engine every time you drive. It's the balanced equation for burning gasoline, and a version of this reaction is happening millions of times a second all over the world. The really important part is hiding in plain sight, right there in those big numbers, the coefficients. The balanced equation tells us something incredible. For every 2 tiny molecules of gasoline that get burned, the engine produces a massive 16 molecules of carbon dioxide. That's an 8-to-1 ratio. This chart really drives the point home, doesn't it? Look at that comparison. The amount of fuel we start with seems small, but the amount of CO2 that comes out the other end is huge. This is it. This is exactly how scientists can calculate with incredible accuracy how much CO2 is being pumped into our atmosphere from burning fossil fuels. It all comes from balancing the equation.
And of course, it gets even more advanced. For really, really complex reactions, I'm talking dozens of components, chemists aren't doing this by hand. They feed these problems into computers that use something called matrices. It's a tool from linear algebra to solve for all the coefficients in a split second. It's the exact same principle, just on a massive scale.
When you get right down to it, balancing a chemical equation is about turning something that looks like magic into pure logic. It's about finding the hidden rules of a system, making sure that what we write down on paper actually reflects reality, a reality where nothing is ever truly lost. And it really makes you wonder, right? What other parts of our world, from the economy to our environment, could we understand more clearly if we just took the time to find and balance the underlying equation?